From our solution of supersonic flow past a wave, we have extended that solution to flow over an airfoil, and we have seen that pressure coefficient can very easily be obtained from the local surface inclination. So, supersonic linearized problem can be solved quite easily, and this can also be extended to a 3-dimensional wing, because in case of a 3-dimensional wing, say if we have a rectangular wing, as we know from our supersonic flow over wings, we can see that for supersonic flow over a wing, if considering a straight rectangular wing, we know from our study on incompressible flow that because of the tip effect, the lift reduces. However, in case of a supersonic flow, we know that there is a limited upstream influence. Hence, if we have the Mach line from the tip, and hence in a 3-dimensional sense it is a Mach cone, that the tip effect will not be felt outside this Mach cone. So, this part of the wing so tip effect is here only. Within this Mach cone. As a consequence, see this over this part, the flow is 2-dimensional over this part, and the pressure coefficient at any point, and hence the difference between lower surface and upper surface pressure, which we usually call the loading, on this part of the wing will remain as in case of a 2-dimensional flow. So, the loss in lift is only due to this part of the wing, and this part is purely 2-dimensional. For a swept wing, the situation may be little different, and there might be 2 particular cases where both the Mach lines from this tip leading edge are lying on the wing, or one of them is lying on the wing, the other outside the wing, as in this case. So, in this case the situation is almost similar to this, and only the effect tip effect is felt here, and the loss of lift is only because of this part. However, another situation may arise with a supersonic wing. In this type of situation, where both the Mach lines are over the wing and there is a part of wing which is outside this Mach cone, part of wing tip not in the Mach cone. In this type of situation, the lower part and lower surface and upper surface of the wing will not felt the effect of the other, and it is possible to have a pressure difference at the tip. So, pressure difference at the tip is possible in this case. So, in this type of wing there will be decrease in pressure over this part, however, that will again be gained by this part, and if the flow configuration is like this, then it is called a supersonic leading edge. However, in the earlier two cases that we discussed, that is for the rectangular wing and a swept wing in this configuration, these are called subsonic leading edge. And in this case, no pressure difference at the tip. So, in case of a supersonic leading edge, tip loading is possible. However, we will not go for any quantitative discussion of these at this stage. We will now consider some other application of linearized flow problems. See, this linearized flow problems are can be categorized mainly a two dimensional flow, which we have discussed earlier, a planar flow. Of course, a two dimensional case is a special case of this planar flow problem, and a very important application of this linearized flow theory or small perturbation theory is a slender body or elongated body. or bodies of revolution. So, linearized flow problems are broadly of 2D and planar flow, and usually these are bodies of revolution. Now, in this case, consistent with small perturbation theory, the basic assumptions lies that the slope of the surface at everywhere is small, and in particular flow over elongated body, that is elongated along a particular direction, say x. So, that body is highly slender, that is in one direction it is, its length is so large compared to its length in the other direction slender, and boundary condition may apply to the axis. As in case of a 2-dimensional and planar flow, we have satisfied the boundary condition on say y equal to 0, that is normal velocity on the surface is taken as the normal velocity at y equal to 0. So, for elongated bodies also a similar type of approximation can be used. Now, for elongated bodies, cylindrical coordinates are more convenient, and we will try to derive the potential equation in cylindrical coordinate. Now, let us potential equation in cylindrical system. The cylindrical coordinates are as convenience x are theta, and theta locates the meridian plane x r, and let us say we choose theta equal to 0, which represents x z plane. So, of course, the choice is arbitrary. Theta locates the meridional plane x r, a reference for theta is arbitrary. However, as we mentioned, this is arbitrary, we can choose any. So, in our this coordinate system, we have our x 1 equal to x, x 2 equal to r, and x 3 is theta, and the velocity components u 1 as before we will consider as u infinity plus u, that equal to d phi d x. Phi in this case is total potential. U 2 will choose as and similarly U 3 can be chosen as W, which is d phi d theta. So, the velocity component W or u 3 is along the theta direction. So, basically this is a tangential or circumferential velocity. Now, in the derivation of the potential equation, we have seen earlier that we started with the continuity equation, and in which we replaced density using momentum and energy equation, introducing speed of sound, and then speed of sound is further replaced by velocity components using the energy equation, free stream speed of sound and velocity components using the energy equation, and then a complete equation was obtained in terms of speed of sound at infinity and the velocity component, or in terms of free stream Mach number and velocity components, which was then replaced by the perturbation potential, and then further we assumed a small perturbation approximation to simplify the equations, which resulted in the Cartesian equation. So, equivalent Cartesian equations, if you remember, equivalent Cartesian equation where phi x x, phi y y, phi z z are second derivative of phi with respect to x, y or z in the Cartesian system, and phi is perturbation potential. So, we will try to obtain an equation corresponding to this in the cylindrical system. So, first of all, let us consider the continuity equation in the Cartesian system, in the cylindrical system. Let us consider a small unit volume element So, for this small volume element, delta x into delta r into r delta theta, that equal to r delta x delta r delta theta, that is the volume of this infinitesimal element. Now, for the continuity equation in steady flow, we know that sum total of mass fluxes entering minus the sum total of mass fluxes leaving equates to 0. So, for steady flow continuity equation, now let us say consider flow velocity along x or mass flow along x. So, the mass flow along x let us say mass is coming from this side and leaving from this side. So, through this phase mass flow entering is rho u1 into delta r into delta r delta theta, rho u1 into delta r into r delta theta, and mass flow that is leaving is through this phase, again rho u1 delta r into r delta theta plus its rate of change along x d dx of rho u1 delta r into r delta theta into delta x. This is what is the mass flow leaving. So, subtracting this from this is what is the net mass flow rate along x, and similarly we can find the net mass flow rate along the two other directions, and consequently this becomes d dx of rho u 1 delta r delta theta into delta x plus d dr of what we have considered v. Rho v r delta theta delta x into delta r plus d d theta of rho w delta x delta r into delta theta that equal to 0. So, net accumulation within the control volume is 0, and on an unit volume basis, for an unit volume this becomes d dx of rho u 1 plus 1 by r d dr of rho v r plus 1 by r d d theta of rho w equal to 0. So, this is the continuity equation in the cylindrical coordinate system, and we can see here this becomes d dx of rho u 1 plus so, if we compare this with the Cartesian system continuity equation, we see an additional term which is present in this case, and of course, this will give additional term in the small perturbation potential equation also. The subsequent steps are to obtain the small perturbation potential equation is first. Elimination of rho So, using U1 d1 plus V dV plus W dW equal to minus dP that equal to minus square d rho. Once rho is eliminated, which are higher order, that is all squares and cross product terms. However, is that V by R cannot be neglected since R can be small and as a consequence, when all these are applied, the equation that finally we get are as can be seen, this is simply V by R plus 1 by R square where phi is now perturbation potential U is d phi dx, V is d phi dr and W is d phi d theta. We can see that the perturbation, since there was no undisturbed stream in r and theta direction, the perturbation potential, gradient of perturbation potential and gradient of total potential in r and theta direction are the same, giving rise to the perturbation velocities in V and W. So, this is the equation that holds for potential flow over potential flow in x or theta coordinate or cylindrical coordinate system. Now, let us come to the boundary conditions. We have seen in two dimensional case for 2D flow and planar flow, we have seen that dx2 dx1 on the body is u2 by u infinity plus u body, and which was approximated to be u2 at 0 by u infinity plus u 0. That is, we approximated that the u2 component of the velocity and the perturbation x1 component of the perturbation velocity on the body surface can be replaced by their respective values at x2 equal to 0. Since the body is very thin, and so the difference in velocity from y equal to 0 from x2 equal to 0 to x2 over the body is negligible, and this approximation holds, and this also further we approximated that this is u2 at 0 by u infinity. Since this is much larger than this, we made this approximation. So, this is what we used for two dimensional flow. Now, for elongated body of revolution, again the physical boundary condition that the mass flow rate norm through the body surface must be 0, which again implies that the velocity must be tangential to the body surface, or the normal component of the velocity is 0. Now, from this physical boundary condition, we can see that W is tangential by definition. So, the W component satisfies the boundary condition on its own. So, what is required is that vector sum of other two components must be tangential. Must be tangential to the body surface. Now, other two component definitely refer to the meridional plane. So, what we need is in the meridian plane, hence boundary condition meridian plane is now in the meridian plane, let us say the contour of the body in the meridian plane, say r equal to r x hence the boundary condition dr dx is b by u infinity plus u evaluated at r plus r. However, in this case, this we cannot be approximated make this substitution here and further simplify. Now, we will see why this approximation is not possible. Why this approximation is not possible? In essence, see, in case of a two dimensional flow, we made this approximation that the velocity on the surface of a two dimensional body is same or nearly the same as the velocity it would be on the axis. So, that we simply transfer the surface to the axis. This is not possible in case of bodies of revolution or when we are considering the cylindrical coordinate system. The reason is the presence of the term rho v by r in the continuity equation or in the mass flow equation. So, you can see that for two dimensional case, what we have done is that this u 1 is a function of say x 1 and x 2 is simply u infinity plus u x 1 x 2, and if we make a Taylor series expansion of this becomes u infinity plus u x 1 0 plus u 1 x 2 plus a 2 x 2 square plus this is what is expansion of u x1 x2 about x1 0. Similarly, the other component of velocity also x1 0 plus b1 x2 plus b2 x2 square plus so on. And for very thin body, it is possible to neglect all terms containing x 2. That is, in this expansion we can neglect this all these terms, and here also you can neglect all these terms. As a consequence, this comes as u body is same as u 0, x 1 of course, we are not writing here, and u 2 on the body is same as u 2 0. Now, when we come to the cylindrical system, let us say for that XR system, cannot be expanded about r equal to 0, since the velocity gradients are singular. Eventually, it should be noted that these coefficients here, these a 1, a 2, b 1, b 2, they represent the gradient of the velocity component, or rather this a 1 is related to du dx, a 2 is related to second derivative of u. Similarly, b 1 and b 2 they relate to the first and second derivative of u 2. And this velocity gradients are singular. This is due to the presence of the term one by r ddr of V r. However, since in the continuity equation the sum, these two terms sum to 0, so they are of the same order from continuity in the meridian plane plane 1 by r d d r of V r, it is of the same order as d u d x. Or and for small r. Hence, as r approaches 0, V r approaches so, what we find that near the axis V is of the order of 1 by r, and since 1 by r is extremely large near the axis, V is very large near the axis and it falls very rapidly, and hence it is not possible to replace V on r equal to on the body surface to be same V as on the axis, because in this from the axis V approaches to a very large value, almost an infinite value, while on the body surface it reaches to a finite value and the fall is very rapid, extremely rapid. So, from here we can write this V is a 0 by r plus a 1 plus so, we see now it is not possible to take V equal to a 1, which is the case. Hence, this the approximate boundary condition should be, hence the approximate boundary condition should be you see that V we cannot take as V on the body, we cannot take as V on the axis. However, we can take that for V r, and to do that we multiply this by r dr dx that equal to V r by u infinity plus u r equal to r, and now we can make it Now, from irrotationality, we have du dr equal to dv dx, and this implies so on. So, what we have seen today is that we have derived the continuity equation in the cylindrical system, and hence the potential equation in x or theta system or the cylindrical system, and also we have seen that why for bodies of revolution the standard two dimensional approximation of the surface boundary condition or flow tangency boundary condition cannot be applied. That is, the velocity on the body surface cannot be approximated as the velocity on the axis. That is simply because in this case the radial component of the velocity approaches infinity near the axis, it is extremely large, and consequently that approximation cannot, first order approximation cannot be applied in this system. However, we have obtained what should be the correct approximate form of the surface flow tangency boundary condition, and also what should be the general form of the radial component and the axial component of velocity. We will subsequently move for solving some problem of practical interest in our next class.